This video is brought to you by mywayteaching.com.
In this part, let us solve another simple example, that is example 3. The question is, which of the following functions of time represent, the first one is simple harmonic motion and the second one is periodic but not simple harmonic. So given the period for each case. So now let us consider the first one, that is sin omega t minus cos omega t, the first case, and second one is sin 2 omega t. So now let us consider the first case, that is sin omega t minus cos omega t, isn't it? So we can say sin omega t minus, we can write this cos omega t as sin pi by 2 minus omega t, isn't it? And this is nothing but sin A minus sin B, which gives 2 cos pi by 4 A plus B by 2 into sin A minus B by 2, which gives omega t by minus pi by 4. So we can write it as square root of 2 sin omega t minus pi by 4. So here this function represents a simple harmonic motion having a period t which is equal to 2 pi by w and a phase angle minus pi by 4 we can write, or even we can write it as 7 pi by 4. Okay. And the second part of the question, they have given it as sin square omega t. So we can represent it as 1 by 2 minus 1 by 2 cos 2 omega t. And the function is periodic, which is having a period t is equal to pi by w, and it also represents a harmonic motion with the point of equilibrium occurring at 1 by 2 instead of 0. Okay. So now let us study about simple harmonic motion and uniform circular motion. See, the projection of uniform circular motion on a diameter of the circle, it follows a simple harmonic motion. So you can consider a very simple experiment for that. So you just you can consider a very simple experiment. As you can see in this figure, you can visualize this. You just tie a ball to the end of the string and make it move in a horizontal plane about a fixed point with constant angular speed. So you just turn this ball which is tied to a string in a horizontal plane with a constant angular speed, and the ball would then perform a uniform circular motion in horizontal plane, and you just observe the ball sideways, or you can observe it from the front, fixing your attention in the plane of motion. You know that ball, it will appear to execute to and fro motion along a horizontal line with the point of rotation as the midpoint. And even you can observe the shadow of the ball on the wall, which is perpendicular to the plane of the circle. See, in this process, what we observe is the motion of the ball on a diameter of the circle normal to the direction of weaving. Okay. See, mathematically, if you just consider, if a particle P is moving uniformly on a circle, this is a circle of radius A with angular speed W. So this circle is having the radius A and this circle is having the radius B. And the sense of rotation is anti-clockwise. And the initial position vector of the particle, that is nothing but vector OP bar at t is equal to 0 makes an angle pi with positive direction of x-axis, isn't it? So it makes an angle pi with positive x-axis. So, and they cover a further angle omega t, and its position vector will make an angle of omega t plus pi with positive x-axis. So next you just consider the position vector OP on the x-axis. This will be OP dash. The position of P dash on the x-axis as the particle P it moves on the circle, that is given by x of t is equal to a cos omega t plus pi. See, this is the defining equation of simple harmonic motion, and this shows that if P moves uniformly on a circle, then its projection, that is P dash, on a diameter of the circle, it also executes HS, simple harmonic motion, SHM. And the particle P and the circle on which this moves, they sometimes we call it as reference particle and reference circle. And even we can take projection of the motion of P on any diameter, say on y-axis, as you can see here. So we can take that projection in y-axis also, not only on x-axis. In that case, the displacement of P dash on that y-axis is given by a sine omega t, and this is also simple harmonic motion of the same amplitude as that of the projection on x-axis, but differing by phase of 90 degree. See, in spite of this connection between the circular motion and simple harmonic motion, the force acting on a particle in linear simple harmonic motion is very different from the centripetal force which is needed to keep a particle in uniform circular motion. So both are different. Figure that what we just saw, that is okay, the projection on x-axis and projection on y-axis, those figures they depict two circular motions, the radius of the circle, the period of revolution, the initial position, and the sense of revolution are indicated on figures. And now we should obtain the simple harmonic motions of the x projection of the radius vector of the rotating particle p in each case. Okay, first one is the case A and the second one is case B. So you can see in this figure the first case for this and the second case is for this. So the first case, when we consider the first case, that is at t is equal to 0, this OP, it makes an angle of 45 degree, that is nothing but pi by 4 radians with the positive x-axis. So when it covers a time t, then it covers an angle that is equal to 2 pi by t into t in the anti-clockwise sense. So and that makes an angle which is given by 2 pi by t into t plus pi by 4 with x-axis. And the projection of OP on the x-axis at time t is given by, yes, we can represent it with the equation, that is x of t is equal to a cos 2 pi by capital T, that is period, plus pi by 4. And if you consider the time period as 4 seconds, then this equation will become x of t is equal to a cos 2 pi by 4 into t plus pi by 4, which is the simple harmonic motion of amplitude A, period 4 second, and the initial phase pi by 4. Okay. Now moving to the second part of the question. See, in that case, when t is equal to 0, OP makes an angle of 90 degree, that is nothing but pi by 2 radians, isn't it? You can see here. See, this OP makes an angle of 90 degree with the x-axis, and after time t, when it covers the time t, again it makes an angle of 2 pi by t into t in the clockwise sense, and it makes an angle which is given by pi by 2 minus 2 pi by t into t with the x-axis, and the projection of OP on the x-axis at time t is given by, yes, we can represent it as x of t is equal to b cos pi by 2 minus 2 pi by t into t, which is also, we can write it as b sine 2 pi by t into small t. For t is equal to 30 seconds, this will become x of t is equal to b sine pi by 15 into t. Writing this as x of t is equal to b cos pi by 15 into t minus pi by 2, and when you compare this with the equation that we studied previously, when that is x of t is equal to this equation we studied previously, isn't it? This is pi. So we find that this represents a simple harmonic motion if you compare that with the equation that we got just now. So amplitude B period 30 seconds and the initial phase is given by minus pi by 2.